Hi. Hola, Pau. Què tal? Pau, se sent un soroll, no sé si és el teu o el meu. Si és el meu, no sé, algú que s'està connectant.
Trying. Yes. Hi, Eva.
Hi.
Hi, hello. Hello, everyone.
Hi.
Hi, Paul. Hi, Eva.
Hi, hello. I'm trying to... Shit. Have 1 second. Well, let's wait while people connect. Something wrong with no loud. Okay, there we go. Connect. Well, less people around. Joaquim, where is Joaquim?
He must be arriving from his Dutch class. He will be here soon.
Okay. Well, well, you didn't send me the last file. You have it?
The problem file? Yeah, I know. I will send it now in order to we can upload it. I will send it now.
Okay. Well, after the class, it will be uploaded because it takes the server takes always. Well, send it to me. Otherwise,
I will send it.
Okay. So after the class in the website, you'll have the next list. You already have the solutions to the problems, and if you look at if you have a look now at the web page, people are still arriving. So let me, well, say things that are not. I mean, if you look at the web page, now you realize that here, well, I put for the people in China, I keep the videos in the format that you can see it. And then I open a channel, I mean, inside my YouTube channel, there is a reproduction list with the course so far. So you click here, you see all the lectures from the beginning. I have, well, the notes, we didn't update the notes, we should, the notes of the course. Let's say it says regularly, but the definition of regularly was not set. But it will be uploaded. So far, it contains the results of the first 2 days. But while you have the slides and you have the annotated slides of the session. Well, I didn't upload the annotated slides of day 3. I will. And also the annotated slides of today. If you look at the slides for today, you realize that there is too much material. But this is done on purpose because I was asked in one of the sessions about the case of geometric quantization, and I provided and let's say the study of toric actions is a good place to discuss geometric quantization by just looking at the image of the moment map. That's why I added some slides. I know I will not reach that point. This is an extra bonus for the people who ask me. Okay, so now I think, well, we are 25, but I'm going to start. I'm going to start sharing my slides. There we are. Okay. Let me share. So as Paul was saying, the list of problems for next session is still not there.
No, but it will be in a few months.
It will be,
because I'm taking out the solutions in order that it appears that they only appear the statement.
okay, because Paul is very organized and he types down the solutions. Okay, let me see if I can do this without distorting all. I have here this. I don't want to do this. Screen mirror. So they will be after the class. It takes me 2 minutes to upload it on the server. It's me who takes care of this. But the problem is that the server takes X time, X between 30 minutes and 1 hour to update whatever changes I perform, even if I do them directly on the folder. Don't ask me why. It's like that. Okay, now I had downloaded this, but because okay, this is open here. Okay, there we go. So, well, there is too much material, but let me put, because on Tuesday we didn't have the class, I think it's good to make a very short summary of what we need to remember in this space for notes for the class of today. Remember that we looked at the symplectic classification. We had here the symplectic world. Somewhere in the middle, the b-symplectic world. That's a little bit the message. In the last class, we already considered more sophisticated singularities like m-symplectic, and we showed there was a desingularization result. I will get back to this desingularization result, not today. Then we have here the Poisson world, which deserves a different color. Okay, we have like these three worlds altogether. What we have done so far is to explore what we put here in the b-symplectic and compare a little bit on symplectic and Poisson. Of course, symplectic and b-symplectic are inside Poisson, but let's say they are well, the message I want to throw is that they are simplest classes than a general Poisson structure. What we saw, for instance, already here, yes, the first day, is that here we had the Root Theorem. Okay. Here we had classification of surfaces. What we didn't show, and I will today, is that we have some other interesting things going on. Today, we will see that in the symplectic case, and this will serve as a revision. When we consider an integrable system, we have special adapt coordinates such that you can think in this classification scheme, in the same classification scheme of Darboux and classification of surfaces. In the Darboux theorem, you have a normal form theorem. Here you have the same. We will see that you have some action angle coordinates. And action angle coordinates are going to be very powerful because they allow us to describe what happens not on the total manifold. This is too much. But what happens in a neighborhood of an invariant submanifold where action takes place. And action takes place on what is called the Liouville torus. What is the relation between action angle coordinates and group actions? There is a lot of relation. We could think indeed that action angle coordinates, the existence of action angle coordinates themselves can be seen, or you can even, this is the famous, the theorem that arose, this is classically known as Arnold-Liouville. Now that Boris is not connected, I will say that I will call it Arnold-Liouville-Miner, because Miner had to do a lot in that theorem. Indeed, he was the first to exhibit the formula of the action functionals that you find in the book of Arnold. But first you find it in this paper in the Cornell Polytechnic by Henry Miner. So that's a little bit the scheme. So the scheme is that these guys are related to group actions. And indeed, I will use group actions to make this proof. And I'll try, then this is the symplectic case. As you see, this is what I want to explain today. When I consider group actions, what is closer to actional coordinates and what is closer to integrable systems is called toric actions. Toric actions are actions where I have my manifold, my symplectic manifold has dimension 2n, and where I have a tonus or a torus that acts of dimension n. And this torus acts, as we will see, and this is to be defined, in a Hamiltonian fashion. Intuition tells me that in a Hamiltonian fashion means that the fundamental vector fields of the action are Hamiltonian. This is correct. But there is more or less another requirement, which is that we put a certain order altogether of these Hamiltonian vector fields. And we do this using what is called a moment map. So today we will look at this in the symplectic case, and then we will copy it in the m-symplectic case. That's the plan for the day. But let me see, there are things that we have seen already in the b-symplectic case. First, the Darboux theorem, it's a b-Darboux theorem. And I told you that we could achieve the proof in two different ways. One was via the path method, and the other one, this is possible to do, and you can check, well, this is in the notes right now, you can find the b-Darboux theorem, but you cannot find the proof. There is not, I think maybe there is a sketch of the proof, but you can find this in my initial paper of this with Victor Guillemin and Ana Rita Pires, which is a paper in Advances in Math back in 2014. And I think that this is already available online for everyone. Otherwise, the version in the archive, I would say that it's the same version as the published version. Maybe there are some commas or points, but the contents are the same. And there we provide two different proofs of the b-Darboux theorem, one with the path method and one using the method of proof of Alan Weinstein for what this splitting theorem that we have here, because here in the Poisson realm, the analog is the splitting theorem, as you remember, which is due to Alan Weinstein. That's where we are. There's something else. This classification of surfaces in the case, in the symplectic case, I was to here. Well, let me erase this. And this classification of surfaces classification is done using the class of the symplectic form, because the symplectic form is closed, therefore it's a cocycle in the RAM cohomology. So the guy who governs this classification is the RAM cohomology. We saw, maybe too quickly, and that's important, that in the two-dimensional case, the classification of surfaces can also be encoded as a class, as a cohomology class. But this cohomology class is no longer the RAM cohomology, is what is called B-cohomology. Okay, and indeed the classification of surfaces was already done by Radko using the language of Poisson geometry. And what we did with Ana Rita Pires and Victor Guillemin is to provide a language of a language in cohomology to state this theorem as Moser theorem, as Moser did the proof in the symplectic case. It's the same proof. So here we also have, and this is something I said very quickly, and if there are questions about this, I won't regret going over this and also maybe adding a problem in the list, by the way. Yeah, I mean, we have the list and now I'm saying already adding a problem in the list. Well, maybe I'll comment as well. So we have classification of b-symplectic surfaces And the class, and this is something I will use today. They are given by another class, by the class, but now it's the omega is a B form. Remember that the most important thing that I explained last Thursday, is that we have to change our glasses and look at these Poisson, simple Poisson structures, which are called B Poisson, as B symplectic. And we are more comfortable with the new glasses. And the reason is that there are much more results of classification in symplectic geometry than in Poisson geometry. And one of the main techniques that has made this possible is the path method. And the path method does not work well in Poisson geometry. That's the reason why. So let's say, to say that the classification is given by a B form, and this is a restatement of the RAM of Radko classifications theorem. I'll go back to this statement. Indeed, this statement is in violet in these slides later on. And this statement, the good news is that Matteo-Melrose formula gives me a way to say that if omega belongs to the second B cohomology class of the surface, and this cohomology, which I showed, well, I didn't prove, but I showed, it means I presented the result, that this is the same as Poisson cohomology of the surface. And that's a victory for Poisson geometry, because there are not so many examples where Poisson cohomology can be computed. And now in the new books in Poisson geometry, you can already find this result, which is very nice. And for instance, in the new book of, and now I'm making propaganda of a new book that it's published last week, which is a book by Riloja Fernandez, Marius Kreinig, and Jonas Marcoux. In that book, you can already find this as a new example of classification. So now it means B-symplectic geometry is now part of the history already of Poisson geometry. And this is very exciting for me because I proved this theorem. Right? Okay, so this is, as I said, we can now look at this, and this is isomorphic. I can express this in terms of the rank homology, okay? And this is the RAM homology, the second RAM homology group, plus H1 of Z, the critical set. That's what we did, okay? There is no space for what I need to do, but what I will do is to copy these guys in the list. Today, I'm going to focus on this thing. I'm going to focus on actional coordinates for symplectic and B-symplectic. So first I will revise the symplectic case. Why? Because I'm going to use the same method of proof, very close. It's not exactly the same method of proof, but it's very close. I wouldn't say we are going to copy, because copy means to just write down the same, but we are going to mimic, that's the word, the proofs in symplectic geometry with the symplectic glasses. And we will prove an action angle theorem. We will define what toric actions are, and we'll talk about moment maps. And all this, well, in the general, and what's very exciting is that, well, in the general Poisson case, all this is unknown. I mean, there's no way you can find, of course, I proved long time ago in 2011 with my colleague Paul Van Aken an action angle coordinate for Poisson. Okay, but let me see, this was not the most possible general Poisson. We were considering a point where this foliation that you have for the Poisson structure is of maximal rank. This means that in a way, we were considering the foliated case of symplectic geometry, more or less. We can think about this. So let's say that result that I proved back in 2011 doesn't consider singular leaps. But what is very exciting is that the result that I will explain today, in the eyes of a Poisson geometer, looks at the singular leaps. And that's complete novelty. This is a result that indeed it's quite recent. Well, recent, depending on how you look at the word recent. This is a result that it's part of the contents of a thesis of a student of mine. This is something we proved together with Anna Kissenhofer, and who, by the way, got the gold medal in cyclism in Tokyo this year. So she's a mathematician now working at EPFL, but she's also a gold medalist. Can you do this? Well, I would say that this is very hard, but she could do this. So, you know, if you want to do mathematics and sports, you should talk to her. But okay, today, I mean, of course, there is something in common with mathematics and sports is that you have to be very flexible. And today we're going to be totally flexible to be able to prove this result. That's the plan for the day. That's what we did. This is where we're going to. And quantization, it's a very nice ingredient to add to this list. This was not, quantization was not in the list of what I wanted to, of what initially I wanted to explain, okay? But I cannot refrain to say that quantization comes here like an external bubble in a natural way. Why? Because it's possible, once you have these moment maps, we will play linear algebra with the image of the moment map. And the image of the moment map, you have a very difficult manifold. This manifold is complicated, but the image of the moment map is a polytope on Rn. And with polytopes, we can play in many different ways. One thing we can do is to count the integer points inside the lattice and the integer points on the lattice that are inside or on the boundary of this polytope. And this is what indeed quantization does. Okay, if there is somebody working in quantization in the room, they say, no, quantization is not counting points. It's very difficult. It's representation of spaces. Yes, whatever. But at the end of the day, we can prove that it's counting points. And that's fantastic, because who doesn't like to count points in order to compute some representation of spaces? So quantization would be the perfect ingredient if this class lasted for 4 hours, but it lasts for 1 hour and a half. So it has to be the guy in the closet. And that's why there are some slides which are in light red at the end that address quantization. I don't know, maybe it's a direction I can discuss the last day. But today we are not going to have time to go to this, but to say that it's closely related. So as I said,
so this is deformation quantization or geometric quantization?
Yeah, I will talk, Raju, I can even recognize your voice now. That's a very good question. Which quantization am I talking about?
Right.
I could say I'm talking about geometric quantization.
Okay.
But then a second question that Raju could ask me is, okay, but are you talking about formal geometric quantization or geometric quantization using polarizations? Which is because there is a notion of formal geometric quantization that was introduced a long time ago by Mainbrenken and Weizmann. And the magic is that Paul Mir, who is here doing the problem sessions, together with Paul Mir and together with Jonathan, we prove that it's the same. So the question is, doesn't matter. But the formation quantization is a different aspect of the theory. And thank you, Raju, for bringing it up, because I must say that Richard Nest already computed the formation quantization of m-symplectic manifolds, but you will not find it under this name. So it's possible to consider the strict quantization. In the slides, I didn't put the formation quantizations, but I consider formal quantization, which is a model that, if you like representation theory, I know many people connected here like it, then that's a good thing, because you essentially think that you have a group action and delegate everything to your group action. Whereas when we consider quantization given by geometric quantization, we need a polarization, okay? This polarization, okay, So Raju, this polarization.
Okay, I will have a look. Yeah, I don't want to distract you from the main course of action.
Yeah.
Please.
Well, no, but this is a very good question. By the way, Raju, I looked at the Penrose paper, okay, and it's amazing. The answer is yes. There is a B structure in the Penrose paper, and you will not expect its content. It's exactly what you were asking me the first day. So you made me several questions during the course, and the first day you asked me, can you put a contact structure in a general relativity? And another day you gave me this paper of Penrose, and you asked me, can you put a singularity there? And the answer is, and you're going to like this, I can put both a singularity and a constant structure on this example of Penrose. And I was very thankful because this example, we need, as I said, we needed example. It's good to have examples. As you see, the next session is about big contact. So I will briefly describe how you put this contact structure there. The answer is the unit cotangent map. So Raju, thank you for asking your question during the course. Your questions have inspired me, indeed, I must say.
Thank you.
So it's very good questions.
My pleasure.
Thank you.
Eva, I wanted to add, sorry, Eva,
Yeah.
I wanted to add that now that you commented about geometric quantization and Russell 2, we didn't put any problem on geometric quantization, but maybe we could add now a problem about computation of geometric quantization via shift homology. But I don't know if you want to enter or comment about this, and if it's necessary to add a problem that for anyone who wants to try to enter in geometric quantization, we could add another problem in the list.
Wow, this is good because we have this list indeed already ready. We have this problem ready. We have Pau and I have been giving several courses around the world, and we did a course on quantization, so we have this ready. This can be an appendix. This is a good idea, Pau, indeed. I don't think today I have time to get there. That's why I put the slides and people opening the file. It says 61 slides. Is she crazy? No, I know I will not touch everything. But I think this can be a good idea, Pau. We can put an appendix. Appendix is a list of problems that you may want, I mean, for people interested in the topic. I think this is good. You can even provide the solutions because we have this completely written down. That's a good idea. Thanks. Wow. And thanks, Raju, for your questions and your suggestions. As I said, like my students know that I was very, when you send me this reference, I sent an email to everyone saying, look, Raju asked me this question. Let's look at this paper. And then my students started to receive emails very late in the evening at 2 a.m. Well, not later than 2 a.m. probably, but very late, saying, oh, I'm very excited because this and this and this and this and this and this. And so this is very rich. I'm really thankful. Okay, now I'm going to talk about this classification scheme given by the Dalsan theorem, because let's say if you are here in this course, if you have survived after this course, is that more or less you are following. But some of you maybe are more used, let's say, not so used to these complicated problems in differential geometry, but you like a lot linear geometry because you are used to this from school, from the college, I mean, from a university. Like imagine maybe, I mean, Chung was telling me that there are people who are undergraduate following, and this is amazing, and I'm very grateful. So this goes to the undergraduate. We all understand what is a polytope. It's this. That's a polytope. Okay. Here is Dusa-Magdaf. Okay. What's the relation of Dusa-Magdaf in this picture? Dusa-Magdaf, I have told you many times that this classification scheme in dimension 2 that tells you that it's enough to consider the cohomology class doesn't work in higher dimensions, not even in dimension 4. And Dusa-Magdaf gave a counterexample to that classification scheme. That's why I put a picture of her here. But let's focus here. What's this guy and how did you do this picture? Well, this is the image of the moment map. I'm going to consider CP2. Let's get used to CP2 because in the list of problems, there are going to be a lot of CP2s. Well, CP2, it's a sphere, okay? You can think that it's a sphere. You can think of it as you want. You can think of it from an algebraic point of view. Then you are happy to think that this is CP2 that you consider a T. I mean CP2. Sorry, I said it's in dimension. I mean, what is the dimension of this object? This is dimension 4. It's a complex thing. Okay, it's 2-dimensional, but it's complex. So this is 4-dimensional. This is 4-dimensional. Forget out the sphere thing that I said. I mean, we are over the complex here. Okay, this is 2-dimensional, and now we are considering here these are homogeneous coordinates on the projective space. Of course, all of them complex. And this guy here, as you can see, it's an exponential. It's a complex exponential, and I can identify this as an element of S1. And I think of S1 living inside the complex numbers. I think of S1 as complex numbers of module 1, and this is a Lie group, of course. I said Lie group. I didn't know anything about Lie group. It doesn't matter. It's going to be a group which acts on a manifold. We are not going to need anything else than the definition. And the definition of fundamental, of what is the fundamental vector field, which I will recall. Okay, what I say is that I consider this action. This action, it means that I assign to the couple of point and element of the group, this element in CP2. Okay, then it turns out that when I consider the fundamental vector field generated by this action, this means that I put here, for instance, an additional parameter t, I do the derivative of this, and this gives me what is called the fundamental vector field. In general, if I have a Lie group, the fundamental vector field generated by an element of the Lie algebra, okay, the formula that you have is that this is the fundamental group. I recall this. Notations are varied. Sometimes you put this, and you put that it's associated to an element of the algebra. X belongs to the Lie algebra. This is the Lie algebra of the group. Okay. In our case, you can think that you derivate normally, okay, because it's a torus, so you can think that you can embed it inside some Rn, so it's what you expect, it's the derivative. But otherwise, you have to take the exponential of Tx, and on a certain point on the manifold, I want to look at this on a point, then I apply this. Okay, I do the derivative of this applied to the point P. This is an element of the manifold, and you evaluate this when t equals to 0. And this gives you a vector field. Sorry, S equal to 0. This gives you a vector field that is called the fundamental vector field. I will get back to this. Here, you just think that you add this parameter and you do the derivative, and this gives you a when you do this derivative and you evaluate at 0, you get a vector field, and this is the fundamental vector field. Well, this fundamental vector field is Hamiltonian, in the sense that the contraction of the fundamental vector field with the symplectic form is minus the differential of something. Well, what happens is that these functions here is not any function. We can order them in a collective fashion in what is called a moment map. And that's the definition of moment map will come later, not now. But just to let you know that when I have, if I am in higher dimension, you can classify symplectic manifolds if they have these actions by Tora. And these are called toric manifolds. And this can be obtained from algebraic geometry. If you come from algebraic geometry, using the theory of fans, okay? Fans not in the sense of groupies, but it's a theory in algebraic geometry. If you use the theory of fans, you can get to this toric manifold. So again, now you find some object in mathematics where two people are looking at. So it must be an interesting object. I'm going to tell you more. Not only people in symplectic geometry and people in algebraic geometry are looking at toric manifolds. We said people who are interested in mathematical physics are looking at these manifolds. for many different reasons. One of them, and you have maybe heard of, is mirror symmetry. This is an old guy. Maybe now people are not so interested in mirror symmetries. Well, this is false because there are still a lot of people interested in this. I will not get into this, but these guys are important. For us, they are important because of this classification scheme. And then what I say is that the data is that you have a symplectic manifold, you have your torus, and you have this moment mapping, which you essentially put the fundamental vector fields and you take these functions and you put them. This is a mapping where the components are these functions ordered. You take every generator, okay, of the Lie algebra, you play this game, you get a function and you put it in brackets. And this is a function that whose image is on Rn. What is the magic of this guy? Well, that you started with a manifold of dimension 2m, and now the image is half of the dimension. Natural question. Do these guys have something to do with reduction theory? Reduction theory in differential equations in which you have a symmetry, and each time you have a symmetry, you reduce the number of degrees of freedom. Yes. Indeed, this is a way to formalize this reduction of degrees of freedom, and you can look at this, and I think it's very rich to keep in mind that sometimes what we want to do is to solve a differential equation. Okay, here I say I want to classify because I'm a geometer, but there is a motivation behind. So people in differential equations are, of course, interested in these guys. And the connection is given by integrable systems. In order to talk about integrable systems, I need to talk about the special submanifolds in symplectic geometry. Who are the main characters today? Okay, you have a symplectic manifold of dimension 2n. The main characters of the day are Lagrangian submanifolds. A Lagrangian submanifold, I say, given a symplectic manifold, a submanifold is Lagrangian if the pullback by inclusion, I take the inclusion of this submanifold on the manifold, and here I have a form. Okay, I can, if you understand me, I can restrict the form to the submanifold. If I am a very posh person, I do the pullback by the inclusion. This is the same as, okay, as now I just look at the tangent space along L. That's the thing. And when I say that it's zero, it means that it's zero along the tangent space of L. So this is zero. This means, in other words, that omega vanishes identically at the tangent space of L at point of L. Okay. And in other words, if I think of the symplectic form, I could have started this course talking about the linear algebra, okay? And then I would have talked about what is called the symplectic orthogonal, which is what you imagine. It's the equivalent to Riemannian orthogonal, but replacing the metric with the symplectic structure. And then that's the language where you use. And you say that the tangent space to the submanifold, sorry, this is a typo, this is an L, coincides with the tangent, which is the orthogonal. This is the symplectic orthogonal. Why are Lagrangian submanifolds important? And which examples can I tell you about? Well, if you are on a surface, I say on a surface, and I write always a sphere, but, well, take your favorite surface, okay? Any surface. And now I take a curve on this surface. Any curve, embedded curve, okay? Okay, I could become crazy and take a non-embedded curve. Take any curve here. This is defining for you a submanifold of dimension 1 of something of dimension 2. Is this enough? Dimension is not enough. I need to check that omega vanishes. But what happens is that omega, this is a one-dimensional space, therefore it has to vanish. because omega is a skew symmetric, anti-symmetric. Therefore, omega on the same vector is going to vanish. Therefore, this is the same as to say that the pullback with the inclusion of the curve on this two-dimensional surface is going to be 0. This is the same to say that we don't need to check, it's automatic. Any curve is going to be a Lagrangian submanifold. And I say orientable surface because we don't have the notion, right, of non-orientable symplectic manifold. They are all orientable. An example, it's going to be, and I still didn't define this, and that's why they are important, the fiber of the moment map of a toric manifold. In which sense? When we have a toric manifold, and it's good to have to keep an idea in mind, a picture. What the moment map does for you is to decompose this manifold. What do I have? No, I don't have a space for, I ran out of a space for, okay, it seems I didn't include more space to write. Very close, I thought I had excluded one. Okay, never mind. What I want to say is that the image that you have to have of a toric manifold is, you know, the image is going to be a polytope, and then over each point of the polytope, you have torus. You have like a fibration of torus, a family of torus over the image of the moment map. So in a way, you are, if you have a toric manifold, you are decomposing it in this idea that you have some part of it which you can think of it as linear algebra because it's the image of the moment map, and then you have some torus, a fibration by torus. And this fibration is very interesting, okay? And for instance, while these torus don't need to have all the same dimension, when we are here on the boundary, I may have circles, or I may have like the torus, I mean, what is the pre-image of the points on the boundary? Then they are not necessarily a torus. They can be a cylinder too, okay? But inside the polytope, they are all torus. This has to do with a very interesting field that I will not touch in this course, which is the field of singularities of integrable systems. This is one of my favorite topics to talk about, but I will not talk about them. So whenever we have a singularity, the singularity has to be on the boundary, and then the pre-image changes, and you may have strange things going on in the pre-image. Okay. So you think of this manifold, let's say, well, let's look at the interior. Yeah, I don't want to get complicated today. We have this fibration by toric here. And that's the way you need to think about a symplectic. This is also very connected. This torus lying, this image is very convenient for geometric quantization. Just let me say that there is the concept of Bohr-Sommerfeld leaf in geometric quantization, and that's the common line. If you look at these torus which lie on an integer point of the lattice, then these torus lying on an integer point of the lattice are precisely going to be the torus that you count in the quantization, and they are precisely going to be the Bohr-Sommerfeld leaves. And that's an easy exercise that you can. But in order to define what is a Bohr-Sommerfeld leaf, I need to consider a connection, and I don't want to get there. Okay, well, this picture I was saying that the pre-image can be more complicated is when I look at the more general class, not necessarily toric, when I look at integrable singularities of an integrable system that are not necessarily of toric type. In the torus case, we're going to have this collection of guys. Okay, and then if I have, well, then I can have singularities. Singularities are around, but today I will try to step over the singularities. Let's talk about integrable systems. First, why do we care about integrable systems? Well, as I said, these toric manifolds and this idea that the image has half of the dimension of the manifold comes naturally with the idea of reduction. When you apply, and this is old theory, already Kovalevskaya, whose picture is here, also Lee, and that's why Sophus Lee studied the idea of applying groups to differential equations in order to reduce the number of parameters, okay? And the general recipe that you use in a standard reduction theory, not the one that we will need. I will not talk about mass-to-mass reduction, but it's behind. Generally, each time you have a new information, let's say you have a symmetry, okay, and this symmetry has dimension k. This reduces to U. This means that there is a Lie group of dimension k. This reduces in k the level of freedom. Here in symplectic geometry, magic happens, because once you have information for k guys, you reduce to k. And the reason of this is that, indeed, don't forget that symplectic geometry is modeled over the space of points and velocities. So essentially, why do you gain a double number of degrees of freedom? Because once you are reducing in some direction, you can also reduce the velocity in a way. That's a little bit the way to think of why symplectic reduction, that it's something I could talk about, but I will say it because it's natural in my language, but I shouldn't. Symplectic reduction is the way to translate how many degrees of freedom you lose whenever you have a symmetry. And let's say the Toric case is a fantastic case in which you have a torus of dimension n on a symplectic manifold of dimension 2n. By this formula, this is the optimal case. If we talked about reduction, which we want in this course, we could, then we would get a manifold which is a point, because it has dimension 2n minus 2n. So it's the optimal case. It's the case in which you can solve, in which the reduction gives you the point. If you go back to the initial idea of Sophus-Lie, this means that you can solve your differential equation. And that's why we are going to talk, let's say, the facet, which is not so algebraic geometry, but the facet of symplectic geometry that comes from the theory of differential equations, is interested in solving differential equations. And we call them integrable when we can solve them. That's the main reason. So now, inspired by this count of degrees of freedom, well, we can solve them if we have enough symmetries. And enough symmetries means symmetries up to order n, because we are in the symplectic world. We cannot have, indeed, higher order symmetries. And then if you have n symmetries, automatically, if we would have defined this reduction, we would get points. If we plug this information, this reduction information, of some equation in which you can replace some data with this additional information, these are some equations in which essentially what you do is to replace the y's by some information that depends on x, for instance. Then at the end of the day, you can solve the differential equation, and it's enough to have, if your equations, like here, I said, look, Hamilton's equations, this is differential equation, I want to solve this kind of equations. Okay, that's what I want to say. Then in that case, it's enough to have n symmetries, because you are in dimension 2n. That's more or less the recipe. And then symmetries, instead of talking about symmetries, which is a word that many use for by physicists, what is a symmetry? If you ask a physicist what is a symmetry, he's gonna be white for 2 minutes. Okay, I'm making jokes. They know what is a symmetry. For us, a symmetry is something that we can translate into a group action. Here, a symmetry is something in which the invariants are functions. And we have some invariant functions, and that's the definition of integrable system. We need to have a set of functions which are n, okay, such that they Poisson commute, and that's our, let's say, that's what we need to demand to the function. This condition here that they Poisson commute, remember that we can go around this definition. Remember that if we have a symplectic manifold, this is just the symplectic form applied to the Hamiltonian vector fields. We can play with these equations, and this is just the Lie derivative of f1 applied to f2, to the differential of f2. we can think of this like a leader derivative. And that's why I can talk about invariance. This condition equal to 0 is an invariant condition because it means that the Hamiltonian of the function f, and here is fi and fj, and this is for all ij, is tangent to, if I look at the moment map, well, what we call the moment map, if we have an integrable system, is just put together all the functions. Now, what is a fiber? A fiber is the preimage of a point that is non-empty. Okay, if you like the empty space, that's not your course. Okay, so I will take the preimage of something that I know it's in the image. So that's why I put FP. And I say that this is what we call the fiber. We want to understand what is this fiber. Okay, this fiber, we can think of it as the fiber of these functions, but because of this fantastic condition that we have here, we can think of this as a fiber whose tangent space. This tells me that the tangent space to the fiber is given by the Hamiltonian vector fields of Fn, F1, Fn. Okay? What is this telling? This is telling me that this fiber is the invariant submanifold associated to this distribution. I said distribution and I didn't check that it's integrable because I have checked this before, and not only me, also Pau did this in his class last week. Why can I say that this distribution is integrable? Look, I do the bracket of these two guys, and this is this bracket. Why do I know this? I left this as an exercise. I will put it in red. This was an exercise. And I said, to solve this exercise, apply this. I want to check that two derivations are the same. Okay? So what I do this is to apply this to a function. Okay? And then check that it coincides for all functions. This means that derivations are the same. And so I apply this to H. Okay? And this is an exercise. This is a consequence. This is direct from Jacobi identity. Because this guy here directly comes from this. That's automatic. And this guy here, well, you have the lead derivative. So you have to play xfi applied to xfj minus blah. And as I said, is that from Jacobi identity is telling you that this is the same. This is something that showed up also in the problem sessions. Okay. So that's why, and I'm stopping here because, well, I mean, 1 second for this idea, which is great, which is you take a fibration, and I call it fibration just the preimage of a function, okay? And the tangent space is given by the Hamiltonian vector fields. Therefore, this means that if I take the maximal leaf integrating because of Frobenius theorem, this set, okay, this coincides, which is what we should call the invariance of manifold. And this is what people in dynamical systems call invariance of manifolds. This coincides with the fibers. This means that these fibers are invariants of manifolds. Liouville told us, well, what is known as theorem of Liouville is that these invariants of manifolds are torus, but the truth is that Liouville never proved that. Liouville proved that they are invariants of manifolds, and he did a proof as such. You said, well, okay, but Liouville is famous, but this is an exercise that you are leaving us. Yes, but the language that we have now is very different from the language that Liouville had. Now we had the right tools to leave this as an exercise, okay? But for Liouville, this is a theorem. So I have proved Liouville theorem indeed. I have proved the Liouville theorem that there exist invariants of manifolds, and these invariants of manifolds are the preimage of this guy. What is called Liouville theorem is that these manifolds are torus, and there we go. Well, there is this second condition. I didn't comment much of this, and this is important. this is the condition that I usually call functionally independent. Functionally independent of manifolds. Okay. And well, this condition means that you don't have singularities here. Again, we are going to skip the word of singularities. If you consider the moment map in any case, and you have a compact manifold, you are going to have singularities, that's for sure. What happens, Eva, if you have a toric manifold and you consider singularities? Well, the singularities are precisely the preimage in the boundary that I was talking before. Okay, but let's consider the place in which they are regular, which is the inside of the point. Let's look at examples. Examples from physics. I'm going to couple two simple harmonic oscillators. So the total energy, so that's the phase space. And here one of the Hamiltonians, if I'm in physics, it has to do with some energy, right? So that's kinetic plus potential energy in this language here. Okay, we have the language of position, RDX, and momentas. Position, yeah, RDX and momentas otherwise. Okay. So once I have this total energy, which lies on a 4-dimensional manifold, because it's the cotangent, things happen on the plane. No, remember, with double dimension, you are on the cotangent bundle of 2-dimensional. So you are 4-dimensional. Then you take this equation and you put it equal to constant. What is this? Well, that's a sphere. Which sphere? It's a 3-dimensional sphere. Fantastic. Even a Lie group, for the ones who know what is a Lie group. What's good about this is that, in particular, because it's a sphere, you can turn it, and this has to be an invariant. Now, how do you perceive these first integrals? This is an example of how do you find first integrals of your problem. Well, first, maybe they don't exist. Okay. Why? Because the condition of being a first integral is a closed condition, is that some brackets are equal to 0. Now imagine I take a box, okay? I'm going to take a box here. I'm going to show you. I'm taking this box. This is a nice box, right? Well, what is this box? This is the box of collection of n functions. Okay, this box is an infinity box, but I have this box at home and you don't. Okay, now I'm going to put, now imagine, of course, integrable systems are going to be inside this box, but they are going, but if I put, the probability that I open this box, which is a very nice box, I open it, I put my hands in it. Okay, I put my hands in it, and the idea that I take out an object. This object that I take out of the box, okay, this object here, what is this? This is a collection of m functions, but most probably with probability almost 1, this is not going to be an integrable system. So the big deception comes now when I tell you that when you consider the set of integrable systems, in other words, in the box was indeed over. I have the box to keep the camera up. According to what YouTubers say, you need to have the camera at the level of your eyes. So that's the box. And now I use this box, this infinity box, I use it here to film. But this idea of the box tells you that most probably, if you take a collection of m functions, this will not be an integrable system. Why? I'm just applying general measure theory. Okay, I know that the collection, this condition here, is what we call a closed condition because it's equal to 0. If you want, I can consider this the set of brackets, and what I'm doing is to take a set of functions that satisfy that this set of brackets is 0. And this set, okay, it's closed inside this box. As it's closed, it's given by closed equations equals to 0. And this not only, because this you can have the condition different from 0, that it's dense. This is contained in a set whose complement is dense. This means that this is a meager set. This means that most likely your system is not integrable. That's something to keep in mind. We are doing the theory about systems that are rare, but they are very important, right? Because they are the ones that you can solve. But keep in mind that this class is very small. But so the message is, how do you, well, this class is very small, but sometimes we know that an system is integrable, and sometimes we know because of many reasons. I will not enter in details here. Some of them may be of physical nature. This one is of physical nature. Here I know that this, when I couple two harmonic oscillators, this is integrable. Why? Because I know that the total energy is one of the Hamiltonians, is one of the functions I take, and then this is on a three-dimensional sphere. We are lucky. We have a three-dimensional sphere, which in particular is invariant by rotations. You have a sphere, okay? You don't have an object. You don't have the guys in the sofa. By the way, today, remember the guys that were watching the problem session today, I have them with me. They are watching me. I don't know what's their name. You can choose their names. Maybe in the list of problems, in the class of problems, you will tell me how I should call them. Today they are looking at me. But this object, okay, doesn't have these symmetries. It's very anti-symmetric, okay? But if I take a three-dimensional sphere, this is very symmetric. All right. So then I can take the angular momentum. And the angular momentum is given by this function, okay? And it's an exercise, and this could be an exercise in the list to check that this is zero. So that's how usually you look for first integrals. What's the theorem I was discussing at the beginning is the theorem that usually in books you find as Arnold-Liouville. And here, while I know this is recorded, I know that I found the recordings of Boris, and I know that Boris and I would have a fight over this. How do you call this theorem? Well, I call this well, so you can call it Arnold-Liouville, but then you forget about Miner. And I want to say that Miner is not Miner in the sense that he's not minor. Miner is important in this theory because Miner was the first one to provide the formula for the actions. So I think he deserves a place in this theorem. This theorem tells you, and this theorem is super powerful. Liouville's contribution to the theorem is to say that the set, which is invariant, not only is a submanifold, which is what Liouville really proved, but it's a torus. Fantastic. And then, so he's identifying this pre-image of f of p, and that's the part of Liouville with a torus. But the proof comes all in all. In order to prove that we have that this is a torus, we will construct a torus action, and that's the way that indeed you can find this proof in the book of Arnold. I'm following the order of the book of Deustermatt, but it's the same proof. Deustermatt describes this proof very well in a paper in Communications in Pure and Applied Maths. Okay, and this paper, of course, is after the proof of Arnold. But he explains this, in a general context, not only of actional coordinates, but also abstraction theory. So it's more general. But that's what we have to retain. What is this theorem of actional coordinates? You prove that there exists some coordinates that you call action angle with values when you can think that you have like a cotangent bundle of a torus. You can think that this is the cotangent bundle of a torus, such that omega can be written this way. What is this theorem? We have to think of this theorem like an improved version of the Root Theorem. Now, if you look at a point, of course, the Root Theorem is going to tell you that there exists some set of coordinates, such that you write this in the Darboux form. What is magic about this is that these coordinates are not any coordinates. One of them are angular. Okay, so this is telling you that, for instance, when you take, this is going to be equivalent to the new f. When you take f equal to constant, this is telling you that what you get is a torus, which is Liouville theorem. And not only that, This is telling you, okay, that in a neighborhood of this torus, that the other fibers are also going to be tori. So you have a collection of tori. That's this theorem is telling you. And in a neighborhood, you take one of these torus. Now I take one, and I look in a neighborhood of the torus. I'm going to change my color. In the neighborhood of this torus, what I have is some Darboux coordinates, not only in a point, they work in a neighborhood of a torus. That's fantastic. That's the theorem of actional coordinate. Okay. And well, as I said, the second part, I said the level sets correspond to the Liouville tori. This is the description I make here. So that's a little bit, the picture that we have also in the web page of the course. We have reached the point of understanding that picture. That's the collection of Liouville tori. So we can think that you have a fibration by Liouville tori. This fibration is trivial in a neighborhood of a torus, okay? And you have this collection of, you know that you have the Root Theorem, that if you take the PIs equal to CIs, you have the tori. How do you prove this? If you look at the picture that I made, I say, well, one way to think about the proof. Okay, before doing the proof, I'm going to do the proof, but let me explain very quickly what I'm thinking of when I do the proof. What we want is to extend some Darboux coordinates that we know we have in a neighborhood of a torus. So you may think that, okay, once you have a system of Darboux coordinates here, if you want to extend in a neighborhood of a torus, well, you only need to use this torus, in a way, an action by translation on this torus. What it does now, take this neighborhood and extend it to a neighborhood of the torus just by considering an action by translations. This, what it does for you is that it gives you a neighborhood of this torus, and what it does for you is that it extends these coordinates. But how do I know that my initial system, okay, is invariant by these translations of the torus? That's the whole point. Indeed, that's the idea. This picture is the idea of the proof. What we do in order to prove this is that there exists an action of a torus compatible with my system that moves this Darboux ball all around. That's the idea of the proof. And once you know there exists such an action of the torus, this allows you very easily, this is the first step of the proof, to prove that the fibers are torus. Why? Because the fibers coincide with the orbits of the action. And you know that the orbits of the action, there is a theorem that tells you that are the quotient of the group that you make act together with the isotropy group. Okay? And then, well, what we do, so are we going to consider a group of a torus immediately? No, what I will do is to consider a group by Rn. How do I do this? Here, space 4. I want to explain the proof with pictures. How do I extend this? First, I consider an action that I'm going to bravely define in a neighborhood of R. I'm going to define it on Rn in a neighborhood of an invariant submanifold that I call L. I need to assume that this guy is compact. Otherwise, you will see in a minute why you cannot consider this Rn here. I take a neighborhood of a torus, and what I do is to consider an action that what it does for you is to associate to a couple of elements on Rn and a point, it associates the Hamiltonian vector fields. I take the flow of these Hamiltonian vector fields that are, let's say, which functions I consider. Well, I take the integrable system, okay? So I take F1 to T1. This is the T1 flow of F1. And I compose this with T2, F2, and I compose these 2n. I'm following the natural order that is given here. But the truth, and that's very important, is that it doesn't matter, because this is an action of Rn, which is abelian. So all these flows commute, and that's important in order to prove, and this could be an exercise in the list, prove that this is an action, that this defines an Rn action. That's what you need to prove. Okay. Once you prove this, and this is really an exercise for undergraduates, this is indeed an exercise for master students. Once you have this, you know this theorem when you say that the orbit of the action is the group. This applies for compact manifold, but also for proper actions. Proper actions are actions that have in common many things with group actions that are compact. And I can say that the action is proper because I'm in a neighborhood of a compact invariant set. So I take the quotient of Rn by the isotropy of Rn. And this is exactly the fiber. But I know that this is compact. And then I think how the quotients of Rn are. And this is something that Pablo can tell me. If Pablo is connected, unmute yourself. Pablo, are you around?
Yes, hello, can you hear me?
Yes, we can hear you. Okay, Pablo, there we go. Now you're going to tell me we have quotients of a group of Rn, and this is something you study on the third year, right? How are these quotients? What can I get?
Quotients of Rn which are compact, you mean?
Well, I mean, yeah, of course. Well, in principle, any quotient, and then we will identify the compact ones. Any quotient could be a product of it could be a cylinder, right?
Yes.
Because it has to be a quotient. So in general, it can be a cylinder. That's the best you can get. And then, but you know, if it's compact, then
yes, exactly.
It has to be equal to K.
Exactly, yes.
So you get a torus, right? So I'm going to call this Pablo. Pablo indeed is the one who proved Liouville theorem, not Liouville himself. This proves Liouville theorem. Thank you, Pablo. That's perfect. So Pablo has proved Liouville theorem. This proves Liouville theorem. This tells you that the preimage, that the invariant set is compact. I mean, well, I'm assuming that it's compact, but this is telling you that it's a torus because it could be a sphere. Why not a sphere? Look, because a sphere cannot be obtained as a quotient by an action of Rn. And that's the big point. And that's a fantastic idea that you find in the book of Arnold. You also find it. I'm following Doistermat here. So thank you, Pablo. This is okay. This was attributed to Liouville, but we should attribute it to Pablo because Pablo is the one who did the proof. I will talk about Pablo's theorem when I refer to Liouville's theorem. But Pablo's theorem tells me how is this fiber, but doesn't let me know anything about what is the symplectic structure. But it tells me that there is a torus action. So that's very important because now that I started with an Rn action, okay, and then the next step is to get an induced, and this is a difficult exercise, get an induced Tn action. Indeed, this is in the notes. The proof of this theorem that it's usually taught on the third year in undergraduate, we include that in the notes. This is in the notes, and in the notes that are already handed there. So we get an induced Tn action, and that's difficult, okay? Because in order to get an induced Tn action, there is something called the periods that are controlled by these isotropy groups. And what we need to do is to get an uniformation of these isotropy groups. In other words, we need to do a change of coordinates such that the period is always 1. Once the period is always 1, this action induces a Tn action. And then the only thing you would need to check, well, this is a theorem, but you need to check, and it's difficult, but it's the proof of the theorem that this action is Hamiltonian. Once you have that this action is Hamiltonian, then the only thing you need to do is to take this picture and say, well, then I take, if this action is Hamiltonian, the proof is one picture, which consists in the following. Take the Liouville torus, okay? Now take a neighborhood of the Liouville torus in red, okay? Now, this neighborhood, I take it invariant with respect to the Tn action. It's convenient, okay? Now I take a Darboux ball. And the only thing I need to do is to drag this Darboux ball around to extend this, this system of coordinates in the neighborhood of the torus. And this idea, which is a picture that anyone can have, is the proof of this theorem. What I have done now is to give a sketch of the proof. And well, this is what I have been explaining here in these slides. I can skip them. Okay, so that's the proof of actional coordinates. I mean, you have here written down how you prove that this action is Hamiltonian. First, you prove that it's symplectic, and then you use the magic of cohomology to prove that it's Hamiltonian. Okay, I consider this done. So what is the connection? Again, let's go back to toric manifolds. We have integrable systems, and what is the connection? So the connection is the following, and so what I have proved is that integrable systems, with the proof, finding this torus action, which is Hamiltonian, what we have proved is that integrable systems are semi-locally meaning in the neighborhood of a torus, we could call it Pablo's torus instead of Liouville torus, that Pablo's proof that really proved the theorem of Liouville, because Liouville didn't prove it. Somebody had to prove it. Pablo proved it. So Liouville of a Liouville torus are semi-locally toric. This is what we have proved. We have proved this. Our method of proof of the actional coordinates is a modern one. It tells us that they are toric. But the question is, but then what is the connection? Are they the same, or which class, which box is bigger? The box of integrable systems or the box of toric manifolds? I'm going to answer very quickly. The box that is bigger is the box of integrable systems. Integrable systems contains the box of toric manifolds. So toric manifolds are a particular class of integrable systems, are the particular well-behaved class of integrable systems. And the reason why comes from singularity theory. I will not enter into that because life is short, okay? But that's the scheme. Toric manifolds are inside the box of integrable systems. In particular, if I have a toric manifold and I have a moment map, well, that you didn't say what is your definition of moment map. Okay, my definition of moment map in general for a Lie group is that the condition that I already said is satisfied, that the fundamental vector fields are Hamiltonian and that you put them ordered, but we also required that mu is equivariant, and this is where I didn't want to enter. The notion of equivariant requires to revise something that I didn't explain in this course, okay? Which is, I didn't talk about, for instance, the Poisson structure, very briefly, of the dual of a Lie group. Well, I said this. I said that there were coadjoint orbits, and then if we have coadjoint orbits in a Lie algebra, in the dual of a Lie algebra, which is an example of Poisson manifold, that these coadjoint orbits are symplectic leaves, but then there is something called coadjoint action. I don't want to enter there. Okay, because I don't need it. If I talk about actions, about group actions that are abelian, I can replace, if the group action is abelian, okay, I go to the book where this is defined as equivariant, and I do this. Oh, this is the book of Victor Guillemin. I don't care. I don't need this. I just need to replace this by invariant, because if the group is abelian, which is the group I'm considering, right? Because I'm considering actions of torus. So if the action is a torus, what happens at the end of the day is that it's enough to consider a moment map that it's invariant by the group action. What does this do for you? Well, when you integrate this function, this equation, it's not a secret that there is only one function. If you have one function that satisfies this condition, if you added a constant, it will also satisfy this condition. The invariance condition, what it does for you is to fix this constant. That's all. This constant, if you look at the books, at the book I recommended, which is Anna Canas, you will see that this constant is related to the Lie cohomology of the Lie group. But in the abelian case, this is done in full generality for groups that are not abelian. But in the abelian case, we can just skip this definition and go with an easier definition. We can replace this equivariance, which implies you have two actions and to control them, by invariance with respect to the action of the group. So you just need to say that you get a collection of first integrals of the fundamental vector fields of your action, and you need to say that this is invariant. That's what you need. Then magic happens, and you will not prove it, but this is fantastic. It was Delsan. Delsan had his anniversary, his 60 years anniversary, 2 weeks ago or 3 weeks ago in Paris. Delsan had done his thesis under the supervision of Jean-Michel Mar. I mean, you would think, you young people, that 60 years is very old. Okay, but when you get older, you say, oh, he's only 60. And then you say, okay, but he's old. No, he's only 60. So he's young. But we could say that Delsan did this in his thesis. Okay, so when you start a thesis, if your name is Delsan, you end up proving a theorem that I think is one of the most cited theorems, at least in symplectic geometry. This is what he did for his thesis. For his thesis, he proved that if you have a toric manifold, the image is a moment polytope. And the idea comes from the two-dimensional case. In the two-dimensional case, if we take a sphere and we take rotations on the sphere, the moment map is the height function. Here you take dh wedge d theta, okay? And when you contract partial of theta with omega, you get minus the differential of h. So this means that h, the height, is precisely the moment map. Okay, and of course it's invariant by the group action. So this is a moment map. And the image is an interval. So the idea of Delsan is what happens in higher dimensions. What he proved is that the image is always a polytope, and that this polytope had some conditions on their normals. And this is what is called a Delsan polytope. And these are the same equations you saw before. So this is what Delsan did in his thesis. So you could have asked what he did after his thesis. In your thesis, you prove the Delsan theorem. What do you do after? Do you get the Fields medal? At least that's what you expect. Well, what happens is that Delsan then started to specialize on hyperbolic groups. So his life essentially has been outside symplectic geometry after that. But he did very interesting results concerning a geometric group theory. But I mean, he turned 60, he's in Strasbourg, he's alive. I mean, we are talking about a theory that started in the 90s. And then people got very excited because, you know, this is putting symplectic manifolds, toric symplectic manifolds, inside linear geometry. So one thing that you can start doing is to play. How do you play? If you are a kid, you play, this is like a Lego, and you play with the Lego. One thing you can do is try to cut out vertexes here. There is a wonderful problem in the list, 2 problems in the list about this. And this coincides with something that is called symplectic blow-up. I knew I wouldn't have time to talk about this. This is why it is in the list of problems. This will be dealt next Tuesday. Next Tuesday, we are going to play these things. There is a whole theory behind this. So Victor Guillemin and all his school has been working on these objects since the 90s and completely understood, let's say, the geometry and topology of toric manifolds, which is very important. Okay, let's stop here. So that's the connection. Let's stop here concerning the symplectic part. And that's the connection. One problem that you'll see in the list, so I can easily skip, is that you can state the actional coordinates as a cotangent lift. This is in the list of problems, so I simply escape. And here there is an example. So if you look at the n-body problem, which is took us here to this course, the three-body problem. The three-body problem is not integrable, but the two-body problem is integrable. And which are the first integrals of the two-body problem? Well, as I said, here what you can think of, this would be the picture of the two-body problem, or if you want also called the Kepler problem, depending on who you talk to, is that there you have if you are in the two-body problem, you need two, because you are four-dimensional. Because you need to look at these points with two coordinates, so you are four-dimensional. So you need two first integrals, which are the total linear momentum and the total angular momentum. These are first integrals for you. But then what happens is that the n-body problem, and that's one of the difficulties. This is what I was talking about the box. If you want to, I mean, you are happy, you have these toric manifolds, you can play with them, and then somebody in the rear comes to you and says, hey, but you are playing, what are you playing at? Most of the systems are not integrable. And you look at this person and say, oh, but I did my thesis on integrable system. Never mind, you did nothing. Or you did something of zero dimension in the set of vector fields. That's true. Okay. Well, it's not true that this person tells you you did nothing in your thesis, because contributing to understanding integrable systems is very important. But one needs to understand that we are like Carl Sagan put it, okay? We are little butterflies who think that we will live forever and just last one day. That's what we are in this world. Oh my God, what a message I'm sending. But the message is most of the systems are not integrable. And that's interesting, because if they are integrable, life will be too easy. In particular, the n-body problem is an example which is not integrable in general, when n is equal to 3 or bigger. That's why that example of the three-body problem was especially significant. And that's why understanding periodic orbits of the n-body problem is a complicated problem. Because if it was integrable, we would just use this torus and get infinite periodic orbits, right? So that's what connects integrable system to the problem of periodic orbits, which does not belong to today's class. But this is the natural space for notes, which I skip. Here, I mean, let's talk about now what is the big case. I have 5 minutes to the end. As a language, when I have in purple on a slide, is that this is something I already did in the past, and it's just here for a reminder. Let's go back to b-symplectic manifolds, where we have all these examples. Let's remember, and that's important, that's the summary we need to know about b-symplectic manifolds. Okay, these are manifolds that are symplectic away from a critical surface, and on this critical surface, if one of the leaves is compact, what we have is a mapping torus. So this is in violet. I can skip this as reminder. And what I did last Thursday was to change my glasses, to change these glasses with these horrible glasses, but they are pink, but they are horrible. Okay, let's agree with this. And with these glasses, I see a Poisson structure, and with the glasses of today, I just see a singular form. And I explain how to do this. And this is something I explained at the beginning of the class. Okay, the classification of B surfaces a la Moser can be done, and this is something that we did with Guillemin, myself, Victor Guillemin, and Anarita Pires back in 2014, is to understand that thanks to the Matteo-Melrose formula, we can indeed understand the classification of Olga Radko as a cohomology. Well, that's a summary, but that's very good to see what comes in the next 5 minutes. Let me give you the results in b-symplectic geometry with no proofs. What I'm going to do, because I provided the proofs in the symplectic case, is just to use this reminder to more or less understand. What we need in the b-symplectic case, what we need to do is to extend the number of first integrals. Why? Because if I consider my action to be Hamiltonian, then because I have this critical set where the dimension, where the rank of the Poisson structure is lower, then Hamiltonian means that the maximum I could have would be a torus of dimension n-1. So I need to get a torus of dimension n. Who is this torus? Who is this generator of this torus? I need to add a generator You could say in an artificial way, but it's not artificial. I take the modular vector field that I defined last Thursday, and that you're going to find, where you're going to compute again in the list of problems. This is going to be the first problem in the list of problems of Tuesday. You take the modular vector field. What's fantastic about the modular vector field, remember, is that the modular vector field, I said it, it's the Hamiltonian of the logarithm. So if I take the modular vector field, this is the Hamiltonian of the logarithm of the function. So this, what it does for you is to say that what you need to do is to increase the number of admissible functions. What you do is to copy the definition of integrable system, the same we had in the symplectic case, but now put the new glasses on. Throw away the pink glasses of Poisson geometry. They are no good. Throw them away and put your glasses in symplectic geometry. Now, when you put your glasses in symplectic geometry, the only thing you need to do is to increase the number of admissible functions. So what you do is to essentially add the logarithms here. Is this natural? Yes. If I look here at what I explained about the B cohomology, if you look at the B cohomology business, this is taking the omega 0 in this B cohomology. And the omega 0 in the B cohomology is going to include these log functions. This is what we call B functions. So B functions are going to be functions that are in omega 0 in the B cohomology of the manifold. And these are what we call B functions. These are just a constant times logarithm of f. It has to be a constant plus a smooth function. That is what you need. Example, take the sphere with the logarithm. I mean, take the same example of the sphere, but now what we want is that the logarithm is an admissible function. Okay? Then observe that this is the logarithm, because when you do the contraction with respect to partial of theta, you get minus the differential of the logarithm. This is an example. So the message is, okay, if I take an integrable system on a manifold, and then I have the example of the B sphere, I have the general example. Not only that, this is going to be indeed what we proved with my student who is a gold medalist. You don't need to have a gold medal in Tokyo to prove this theorem. This is, I think, is good news, especially for me, who cannot run very quickly. So you don't need this gold medal, but I can show off. Okay. So with Anna and Jeff Scott, we prove that you also have actional coordinates in the B case. And what we did is to follow the same scheme of the proof, which I could leave as an exercise, as a difficult exercise, yeah. But just what we did is to mimic the proof that I explained in the symplectic case, in the B case. I want to inform you that there is a new invariant here in the house, which is this constant. This constant here depends on the component of the critical set where you are, and may change with the component of the critical set. And that's important. That's an invariant that we call the modular weight, because it's the modular weight. If you know the theory in representation theory, this is the modular weight. If we look, okay, at the, okay, if we look here at this action of the modular weight as a circle action, then this C would be the modular weight. If we think from Poisson geometry, this is the modular class in Poisson cohomology. So this C is an invariant, and it's important. And we can reformulate, and this is another exercise in the list. Hopefully this will be useful because I'm going too quickly, that you can reformulate this as a B cotangent. Here there is the proof, which I left as an exercise because it's. And then what's left to understand is, do you have a Dolsan theorem? Eva, for B-symplectic manifolds. Let me take 5 extra minutes to convey the proof, and then what I'm happy is that we included quite a lot of exercises in the list with Pau and Joaquim. So this will be a good complement to the class of today, in which I stopped a lot in the symplectic case and didn't pay so much attention in the B-symplectic case. Okay, if we look, and that's interesting, let's start with dimension 2, where what you have, a toric action would be a circle action on a surface. A question that I asked my students the first year when they start the thesis, and they always fail, is the following question. I'm going to ask this question now in general. Is a torus a toric manifold in symplectic geometry? Who can answer this question? Who volunteers? Raju or Pablo is there? Pablo knows the answer. I think Raju, who is there? Who wants to answer this question? We have a message in the chat. It's not toric. The one who answers is Joe Palmer. Okay, well, yeah, that's good. Joe Palmer is not, of course, a first-year PhD student. Joe Palmer is a specialist in the field in the study of toric and semi-toric manifolds. So for the ones who never met him, he's following this course. I'm very honored. And he has contributed to this theory. We could put his picture close to the picture of Dolzano. So that's exact. What Joe is telling us is true. It's not toric. We don't have a circle action. We cannot have a circle action on the torus, which is Hamiltonian. And that's the trick. Like, you are tempted to say, yes, of course. I mean, if the torus is not a toric manifold, let's go away. And in symplectic geometry, the torus is not a toric manifold because of the reason explained here. Rotations cannot be Hamiltonian. Indeed, you can prove that any function that you have cannot be Hamiltonian, because this guy here, the problem that we have systematic in this example is that this guy here is not a function. So the torus is not toric in the theory of symplectic geometry. And in symplectic geometry, the only surface which is toric is S2. And I have a surprise for you. This is not the case. This is not the case in B geometry. In B geometry, the sphere is toric. This is the example we already provided. And this is a beautiful picture that I adapted from my friend Jeff Scott, who is a wonderful person, and also in particular, he does wonderful pictures in Pixel. So that's a picture of the B sphere. Okay. If we want to do some kind of polytope theory, what puts me very nervous is that goes to infinity. We don't have, like in the Dolzano theorem, this compact image. This puts me nervous. And the surprise is that, voila, this is the B torus. And let me introduce you to a toric torus, which you cannot find in symplectic geometry, but B symplectic geometry does the magic for you. And then you look at the image, and we get nervous because the image seems to be all of R, right? So if we want to do some kind of polytope theorem, first thing we need to do is to compactify this image. How do you do this? Well, you do this formally, but I'm going to formally, you can change in a way, you can use some charts, but you can do it formally. This is the expression, but let me do it with understanding things. What we do is to identify the infinities, plus infinities and minus infinities. And what we get is that in the surface case, the image is then compactified as such. This would be the interval, the equivalent of the interval in the symplectic case. And here it comes a surprise. The B torus, guys, gives us a surprise. This is the image. The red points correspond to compactifications of infinity. So I take the image, it goes to infinity, and then I compactify. I'm going to ask Pau to spend a while explaining this next Tuesday, because he knows this. He's using it now in his thesis. And this needs, Pau, this needs, I think, 5 minutes of explanation, which today I will not have, but this, I think we can use the program section. The magic thing is that this is not a bomb. It looks like a bomb. It's very funny. But this point is identified with this point. This means that the circle, the image is a circle. So this is a circle valued moment map. Have we seen this before? Not in symplectic geometry with this name. But yes, there is a generalization to have group valued momentum maps. And people like Anton Alexeyev, Anastasia Matvieva, who I think she's still around, she was here at the beginning of the class, have been contributing to this theory. And Anastasia, in her thesis, one of the things she's considering is the circle valued model maps. And in the VM context, so this is fantastic. And Anastasia, in her thesis, is doing one thing that somebody needed to do, which is this reduction theory for V manifolds. This is fantastic. But I mean, this requires a little thought. This red part here stands for the different connected components. Of course, here you have an even number. We learned this from the last class of problems. And this is like the toy model of toric manifold. What happens in higher dimensions, you won't believe me, that it's enough to have the toy model. In higher dimensions, and here I'm going to give you the final result. I mean, the formal way to do is that you can, this is the formal way to do that. You can do, you use the Moser theorem a lot. This was the proof. But let me give me the result. This is the only thing we need for the class, which is that in general, toric manifolds are of two types. They are either a product of a standard symplectic toric manifold with one of the B torus in the previous slide that I showed, or the B sphere. And then in the case of the B sphere, we can also obtain, so we need to think of this polytope like a kind of cylinder over the Delson polytope that you get on one leaf on Z. Okay, sorry. This is this is the polytope. So here you are on Z and you have a kind of cylinder over Z. So, and you prove this with the path method. One interesting thing is that you can also try to do semi-toric guides. Now that I have Joe connected, you can classify also semi-toric of these guys. This is something that Pau has in his, I mean, this is something we are looking with Pau. We have some preliminary results, and this would generalize the classification scheme of Sambu-Nock. This generalizes the classification scheme of Sambu-Nock. And we have also an interpretation in terms of polytopes. But this is still not on the archive. So I don't want to say more, because otherwise I'm showing all the thesis of Pau. So also we have a nice interpretation of these invariants from the quantization point of view. So, but okay, now about the toric case, you have these two cases. So if you want to construct, the magic starts here. If you want to construct b-symplectic toric manifolds, it's enough to look at the image of the moment map and play with this. And you have these two cases. At the end of the day, it's either a product of a B torus with a symplectic manifold, or a product with a B sphere up to some symplectic counting. I'm very proud about the list of problems that we have done with Pau, because this is very thoughtful, and Joachim contains many problems. And I'm very happy about the problems we thought, because with Pau we had been working these examples for the proof, well, not for the of examples in quantization. And then we started, I mean, we worked out some examples that now are in the list. So in the list in particular, you can prove that you can generate these guys here as this was in the list of things that were asked by Cavalcanti, if you have a symplectic structure or b-symplectic structure. Indeed, not only b-symplectic, they are b-toric manifolds. Okay. And that's the end of the class, because what comes after, you will see, changes the color. That's the Wittelsand theorem with a picture. That's what this Wittelsand theorem is. This slide, indeed, I have skipped things which are the proof. Okay. This slide is the only thing you need to go to the list, to the class of problems. But I think that it's important, like this compactification, I didn't explain it in full detail, that Pau maybe spends a while explaining this next Tuesday. So next Tuesday, the list of problems contains problems about this idea of the cotangent leaf, the twisted cotangent leaf, and also we thought, discussing with Joachim and Pau, that it would be, because some of the problems of the former list that are already solved are obstruction theory, and I think that we thought that this is important. Joachim at the beginning of the class will start commenting on the solutions of those problems too. So that's all, because here what comes here, it's another story This is for another talk. This is for another life, as you see in the joke. This is about quantization. There is a connection between quantization and toric manifolds, and it's explained in these slides. These slides are in red because I knew I wouldn't have time. So I stop it here. And if you have questions, please let me know. I'm going to stop sharing. Okay, not bad. 26 people have survived the course up to now. This is great. So, and I know some of you, yeah. Can you talk?
Yes.
Yeah. Yeah, let me know.
I want to know what is a geometric quantization by using polarizations you are talking about.
Yeah. So the geometric quantization by using polarizations is the geometric model. It's an approach to quantization that probably was designed by Constant himself. And the polarization, okay, it's given by a Lagrangian foliation. And that's what we have in common here, because if we have a toric manifold, the orbits, what we have described, it's a foliation that it's Lagrangian, because all the leaves are Lagrangian. So this is what it's called a real polarization. So we are tempted to say, can you apply Constant's approach? And Constant's approach to quantization, his approach to quantization is to define quantization as a cohomology. Okay, you said. And this cohomology is it's a cohomology with coefficients in a sheaf, which is what Pau was commenting before. And this is the sheaf of flat sections associated to a connection. So indeed, well, I have now stopped sharing, but this is in the slides. So you are Zhang Li, right?
Yes.
Yeah. So Zhang Li, thanks for your questions. I was saying that Raju questions were very important. Your questions are very important because they are telling me what is the interest of the class, and this is fantastic. So the connection to what I explained today is that once you have, the definition of geometric quantization is very complicated. You have all these cohomologies and so on. But at the end of the day, there is a result that tells you that for toric manifolds, you just need to take the polytope and count the inter points of the manifold. Let me share again.
Yes.
Yeah, let me share. Maybe I can even share from here, which is going to be quicker
because
I just
Professor.
Yeah.
Professor,
Yeah.
I want to say a question.
Yeah. What do you want?
I found that the knowledge you expressed involves algebraic geometry and mathematical physics. If I want to learn the theory of sympathetic geometry, what mathematical foundation is needed, or what kind of ability should I strengthen?
So you are asking, can you repeat the last part of the question, please?
I found you explain involves algebraic geometry and mathematical physics. If I want to learn this, if I want to learn them, what mathematical foundations is I need to learn, or what kind of ability should I strengthen?
Yeah, that's good. So you are asking that if you want to learn this part in mathematical physics, what is the literature? That's what you want. Okay, that's a good question. Yeah, because it's true that in this course we don't have time. Maybe this is an occasion to do another course now when if I can come to China, I'm looking forward, then maybe I can give a course on this mathematical part. What is a good reference for the mathematical motivation of all this theory? I don't know. I would like to think more about this reference because there are several books in the literature, but I'm going to ask indeed Pau as my student, because Pau is exposed to this literature, what he thinks is the best, because I mean, Victor Guillemin, and this is in the literature here. I think I didn't forget. If I forgot, I should add this. Guillemin and Stenberg. No, it's not here. I should add. There is a book by Guillemin and Stenberg, which is Symplectic Geometry and Mathematical Physics. No, well, Symplectic Techniques. I have it here. 1 second. I have it here.
Okay.
Symplectic Techniques in Physics. That's a book that I think it's good for motivation, but I'm going to ask, yeah, that's a book, okay? But I think there are other books, like I'm going to ask maybe Pau.
Sorry, the question is about recommendation.
Which
for
books would you recommend if somebody wants to have a motivation from mathematical physics? This is one, but maybe there are other better books. What do you think?
I think there's one of Guillemin, Giroud, and Carson, Momo Maps and Coverdisms, which I would recommend. I will write it on the chat.
Yeah, which I also have here. Yeah. But yeah, I have also this book here. Now I'm going to ask Victor to pay me $100 for each book I recommend. Looks like that's the book that I was talking about. Yeah, that's the book. This book, though, it's more advanced. This means that, you know, what is nice about this book is that many things are inside this book. There are appendixes. And yeah, the motivation, maybe this book is easier to read than this book. Which one is easier? Pau, what do you think?
Well, here too.
You have it too. We are connected.
Maybe this one, maybe Symplectic Techniques in Physics is
more.
It's
a better.
Yeah.
Yeah. So that's concerning the question of what I would recommend. And then I wanted to show, since I'm here on the webpage of the course, let me show you the slides of today, which are here. Because the other day, it's good that Pau observed me that there was a problem with the slides, that they were not well. So I put them again. There was a problem with the server. So I wanted to also ask the question of Jiang Li. She was asking about this. I mean, of course, the definition of constant of geometric quantization is something difficult to understand at this point. But an image is worth more than 100 words. So what I wanted to show you now is this image, okay? This is in your slides. And this image is the image of a polytope. This could be, if you take, for instance, S2, okay? S2, if you take the symplectic manifold, the product of 3 spheres. Now I'm talking about the symplectic case. Then the image is a cube. And this is the Dalsan polytope. The manifold is the product of 3 spheres, 2-dimensional, and the image is a cube. And then what is easy is to count the points inside this image, which correspond to an integer value, because this cube is inside a space, 3-dimensional, and then you look at the integral points, and they are marked in green. You can count them. 1, 2, 3, 4. How many do we have here? It seems to have 1. I mean, this one is on the facet outside. There is only one which is inside, which is this other green. And the other ones are on the facet. Okay, this computation gives you the geometric quantization for toric manifolds. So in the case in which the polarization is given by a toric manifold just by this Lagrangian foliation, the quantization is just counting these points. How to prove this is magic, okay? And Pau knows this proof by heart, okay? Because we are doing also the V version of this theorem with Pau, and it's very interesting. And I think that this is a good answer to the first question.
Yes.
Okay, are you happy with this?
Yes. I have another question. When we talk about toric manifolds, I don't understand what is the moment map for the t-square action on CP2 like this.
Yes. Yeah, I mean, because I went too quickly. I want to click. I have to criticize myself that I always prepare talks. If you tell me 1 hour and a half, I prepare talks of 3 hours. My students know this. They come to my office. Now, yesterday we were with Pau in person after many 10 years, no? And we were supposed to be for 1 hour and a half, and we were there for 3 hours. This happens. So the truth is that it's normal that that example, I didn't go so much into detail. Okay, that example, and this is
yes,
good, Janli, that you brought this up. I mean, Janli is asking, I don't see what is the moment map of that example. Okay, this indeed is not an exercise in, well, is it this Pau in the list? Yeah, because you put the Hirzebruch surface, okay, and then in order to get the Hirzebruch surface, you need to cut. I'm talking to Pau. You need to cut one of the vertices. So you needed to start with the example of the triangle, no?
Well, we put some examples connected with this. In fact, we asked, not directly, but we asked to construct a manifold which is B toric from symplectic cutting. So this is one question, and we have put some conditions. For instance, that it has 6 fixed points, meaning 6 vertices in the Delson polyton.
Yeah, but you didn't do, let's say, what Janli is asking.
Yes.
Is to do the computation, and I think that this is something that is easier because it's almost there. Okay, what I didn't do today in the example here, this example, I said this gives you we to compute the moment map here.
Yeah.
Okay. This is a computation that it's easier. Indeed, this is, I'm going to tell you more. This example is done in the notes, because this is an example that explicitly I wrote down the moment map. And the moment map is just the sum of the squares of the components. Well, depending if you write it in affine coordinates or in here, this is written in homogeneous coordinates of the projective space. Okay, if you write it in affine coordinates, you need to divide out. And if you look at the notes, there is the moment map. But I think that Janli is making a very interesting point, Pau. And I think that when you do this exercise, when you solve this exercise next Tuesday, or even now, we could compute the moment map for this action, because this is what gives you the triangle. I mean, discussing with Pau, I mean, there is a very interesting toric manifold that you get from here by chopping off, which means cutting this vertex, and it's then you get what is called a Hirzebruch surface. And if Hirzebruch is around, it means that there is algebraic geometry. But well, the first point, and what Janli is asking, is how do you compute the moment map of this action? Okay.
Yes.
Well, and the hint is, what you do is you take a parameter, you put a parameter here of a t, okay? Then you put here a t, and you do the partial derivatives. Then you get a vector field. This vector field, what you do is to contract with omega. Now, good question. Janli is asking a good question. What is the symplectic form that you are using? Okay, I didn't say this, but we are on CP2. We are going to use the Fubini's metric. We are going to use the standard symplectic form dz or wedge overline dz, Pau. And then we just need to contract this form. Well, this is an exercise. This is indeed what Janli is asking me, is what I explain in my class, in my master course every time. This is an example that I have the computations. Pau has the computations because he was attending my course. And I think it's good to add for these explicit computations. And for Janli, I said, okay, just let a parameter t, do the derivative, then you get a vector field. Then in order to find the moment map, you just need to contract this vector field with a form, which is dz over dz over line dz. I mean, the conjugate.
Yes.
Okay.
Okay.
Maybe it's more convenient to write down in a standard coordinates. Okay. Indeed, I'm going to tell you a secret, Janli. This is in the notes, done in the notes, this example. I mean, not the whole explanation of the solution. So you can check, you can try to do this computation and check if it's okay by looking at the notes. In any case, Pau, when he does this example in the list, in which we start with this example of CP2, then he will do all the rest, no? I mean, then he will do the computation. I think, Pau, what we are asking, what Jenny is asking is very legit. She's asking to make a concrete computation.
Yes,
Like
yes,
with Pau,
we
we got used, Pau and I got used to playing with the moment maps, but then yesterday, precisely when we met, we realized that in one of our problems that we were working on together, we needed to put our hands in the computations, right? And then it's when interesting thing happens. So sometimes it's good to do this computation. So let's do these computations explicitly next Tuesday, okay? Okay. I think that,
it will be the first part of
Pau is asking, yeah.
Construct some surface then. So it will be the first part in the exercise to compute the moment map in this case of CP2.
In the case of CP2, yeah. That's good.
Sorry.
Okay. Thank you, Jangli, and thank you for your questions. Well, it's fantastic that there are.
Professor, I have some question to ask.
Okay.
I have read an article says that symplectic geometry is often called symplectic topology. But why? Could you explain it to me?
Yes. Yes. So I mean, you are Hugh Yang Yin. Should I call you Yin or you Yin?
Yeah.
Okay. So Yin is asking me a fantastic question. She's saying, you are talking about symplectic geometry, but nowadays everyone is talking about symplectic topology. Can you explain the difference between symplectic geometry and topology? This is an excellent question. And I'm very glad you made this question, because we have a top expert here in the room in symplectic topology. What is the difference between symplectic geometry and topology? Symplectic topology is, let's say, a way to look at the symplectic objects from a topological point of view and try to see how far you can go just with the topology. That's even, I could say that's even a way to look at the problem. And let's say will I talk about symplectic topology? Yes, it's in the plan. If you look at the plan, Yin, next day, I'm going to talk about the Weinstein conjecture.
Yeah.
I don't know how I will dress. I will dress up because this is a big theorem. The Weinstein conjecture, I will need, to dress in a specific color for the Weinstein conjecture. It's a big conjecture which belongs to what is called contact topology. And what is the difference? The difference is that you want to know if you can say things about your structure, your symplectic structure, or your behavior of your manifold, just looking at the topology. So, in other words, can you construct some kind of new cohomology that captures this? More or less, this would be the philosophy. And this new cohomology, as it happens many times, there is not only one. There are several of them. One is contact homology. Another one is Floer theory. What I'm talking now is something that I will just give a hint, an introduction. And here in the room, we have a top world specialist in the topic of symplectic topology, who's Joaquim Brugués.
Yeah.
Joaquim Brugués, do you want to add more things to my very special definition of symplectic topology? Because Joaquim, his thesis is about precisely Floer homology in the context of B forms, in the context of B symplectic geometry. So can you say something else to this definition that I tried to give, from a philosophical point of view? Joaquim.
It was very instructive. I would just say, indeed, symplectic topology, I will even characterize it as the subset inside of symplectic geometry that tries to derive information about your system from the information that you have on the manifold, right? So that's why exactly. The topology. Of course, when
But
you develop
nowadays,
the theory, you
I
go
agree with
in
you
the
that it's a
opposite.
small set, but if you tell this to Hofer, he will shout at you. He will say, no, symplectic topology now is the important thing, no? Like, yeah, I agree
Are
with
we
you.
recording this?
We are recording this. We are still recording this. And remember that Hofer, maybe I'll try to put him in your jury thesis. But I can cut this in the, if you want, in the version I put online. I know how to cut this in YouTube.
Yeah, what
So
I wanted to say.
That's a very convenient. That's a very convenient definition. Exactly. So Joaquin gave even the definition of what is symplectic topology. So let's say, in other words, for Yin, in order for her to have the idea, let's say this would be a more advanced topic. Okay, this would go. I mean, nowadays everyone is looking at this symplectic topology. Like people working in things in symplectic geometry. Nowadays, what is popular and it's important and everybody's trying to understand is this kind of things. Exactly, Joaquin gave the perfect definition. We want to infer information about our system from some topology. And this topology has to be inside a cohomology, okay? And this cohomology, for instance, is Floer homology. I reserved the last day, if you look, there are open problems day. And this is one of the main topic I wanted to discuss was the one of Floer homology. Okay, in which things are very well understood. Well, I would say very well understood. Still, some of them are still to be understood in the symplectic case. But what about the singular symplectic case? And that's indeed what Joachim is doing in his thesis. Let's say he's like now I think he's one of the, well, at least in our group, he's the top specialist in this topic, I can say. Because he has a total, I mean, the techniques that you use in symplectic topology are very analytical. That happens many times when you start, with this point of view as an undergraduate, that everything are separate boxes, okay? But then one day you realize that doesn't make, right? That these boxes are intermingled. So there is a lot of analysis in symplectic topology. Don't think that you can do it with your hands. There are intuitions you can do with your hands, like in topology, but then there is analysis. And indeed, when Joachim was my master student, he came to me and he said, Eva, I want really to do something in analysis. That's what I like. I said, are you sure? I asked twice, are you sure you really want to do this? Okay. Then I give you this B Floer thing. And this is, well, this is a big world that we are starting to understand with Joachim and Cedric. We are also working with Cedric on this, and soon with Sonia and so on. So it's very fantastic. So Yin, your question was very appropriate. It puts the framework to what we are doing. We are working, let's say, symplectic topology is part of symplectic geometry, but it's so modern that I will say things about this in my last session.
Professor, I have a question.
Okay.
What is the relation between action angle coordinates and canonical coordinates?
And the second coordinate, you say action angle coordinates, and the second one?
Oh yeah, canonical
canonical coordinates. It's the same.
Yeah.
I mean, yeah. So the books in physics, this is also a very good question. People in dynamical systems often call them canonical. So what does it mean, canonical? You know by now, canonical can mean anything. Okay, when we say canonical coordinates, we mean action angle coordinates or Darboux coordinates. In the books which are more in dynamical systems or people in physics, we use this expression canonical. Talking about books, I'm going to recommend a book which is one of my favorites. Which is not here. Where is it? Yes. Talking about books, I want to complement the question that you asked before about books. Pau left in the chat reference for one book. I want to to the list of books that are interesting for mathematical physics and symplectic geometry, in my opinion, this book, which was initially published in German, and now it's in English, it's Mathematical Physics, Classical Mechanics.
Yeah,
This is a big,
fine.
yeah, that's a big book. It's very big, no?
Oh,
This book is fantastic in the sense that if you want to have motivation from this problem from a physical point of view, that's the book. But that's a book that sometimes you have books in physics that neglect symplectic geometry. This book has sections on aspects of symplectic geometry, for instance, KAM, very well explained. It's by Andreas Nauf. It's a book of Springer, and I was not paid by Andreas to make propaganda of this book. But what the truth is that Andreas sent me this book as a present, and I really appreciate because I think this is a must book. Probably this book is easier to understand than this book. This is a good combo in mathematical physics, I would say. This is a book to add. I will add it to the bibliography.
okay.
It's in the bibliography of the master course because this is in the collection Unitext. It's a big book because Andreas now is a guy when he starts writing, he writes long papers and so on. But it's very good. It could be three books of 3 different aspects, and it would be easier to read because it's quite big. That's a good reference. That's a fantastic reference, I would say.
Okay,
From
I
a-
will read it. Oh, okay, thank you.
Thanks. Okay, guys, thank you very much for still being there after all these sessions. I know
Hello,
it's
I
hard.
have another question.
Yeah.
Can you explain why the bracket of L and H is 0?
What is the bracket of R and
L and H is 0.
H0?
L
Which bracket?
L and H, the bracket of L and H.
Ah, okay. In this example, yes. Let's go back. Let me project. This could be a problem in the list. Indeed, it was not a problem. Let me project 1 second. Okay, that's a very specific question, which makes me think, guys, Pau and Joaquim, that we should add this problem to the list. Okay, because it's we should add some problems of specific computations. Okay, let me share. That's a good question. So what he's asking is in this example.
Professor, I have a question. 就是 the Liouville-Toric theorem is mentioned on page 7. What are the applications of this theorem?
Other applications of the actional. I mean, I will go now to the example that was asked by your colleague, but other applications, and an important application I initially wanted to discuss, but finally I didn't discuss. It's a theorem on perturbation theory. It's KAM. Kolmogorov-Arnold-Moser theory. It's about now you have an integrable system, now you perturb it. Will your torus survive? Okay, that's indeed a very important application of actional coordinates, because once you have actional coordinates, you can control these perturbations and you can check how is the set of torus that are that survive. Initially, this is in the plan, but finally I realized that this was too much for this course. So this would be this would be like an appendix of the course, the KAM. This would be an application. Let me.
Thank you.
Okay. Let me go to the question of your colleague, and that's very good. So your colleague, now I'm going to share. One second. Let me share. Thank you for the questions. Your questions are helping me indeed to know like how I should, think of the class. So we have this question from the audience. Here we have two harmonic oscillators. So the question is, why is this bracket 0, L and H in this example?
Oh.
Okay, that was the question we got. Yeah, that's example, right? You were asking me. So here the structure, that's the symplectic structure, okay? So when we do, so look, the bracket L and H, I can look at it as the Hamiltonian of L against H. what happens is that the Hamiltonian of L is this vector field. This vector field means that if I write this as a vector field, it's going to be minus x2 partial of x1 plus x1 partial of x2 minus y2 partial of x1, sorry, partial of x2. I mean, I need to take this in, sorry, partial of x2 plus y1 partial of y2. I'm taking these coordinates, and this vector field is taking in coordinates x1, y1. This means that this is the coefficient of partial y1. Okay, so in order to check that the bracket is zero, by the we have two ways to think of this.
Okay,
the first one is without computations. Without computations is this: if I take h equal to constant, this is invariant by rotations. This means that the bracket of these two guys has to be zero. This is the physical way to do it. Now let's do it with a computation. Once you have this vector field, you just need to apply this vector field to, this is x of L, you need to apply it to this function. And then you check that this is zero. How do you do this? Well, you have minus x2 partial y1. This is going to give you this derivative with a minus. This is going to give you minus x2 plus x1, because these two cancels out with these two. I'm saying it without writing. But Paul, let's add this problem to the list. Plus
Okay,
x1, let's add this problem.
Okay.
Plus
Thank you.
x1. No, but you see, I think this is a very good question. I'm very pleased with this question, because this tells me that we need to include this in the list of problems. We need to check this. So you would do x1 partial x2, okay? Then what happens is that x2 gives you a plus x2. When you do, sorry, this is y1, then you get x2 plus y1. And then you get here the minus. So you have cancellations of the terms, and you get these two terms, and then with a minus sign. You agree with me? Well, in any case, I have said how to do this. This is a good exercise because not everyone in this course has the same level. So I think it's good to provide actual computation. Okay, thank you very much for the question.
Okay, thank you.
Thank you. So we will, we're going to, now I told you how to do it. What's your name? Sorry. Can you tell me your name, the one who just asked? Okay. Well, in any case, we will include this in the list. And if you want to do this on the...
My name is Liang Mengxiang.
Okay. So I should call you Lianong Xiang. Okay, so next day, we can start if you want. Did you understand how to do this? Because we will include this list in the problems. If you want to project the solution and to explain to the other colleagues, would you like to go on the whiteboard next Tuesday or not? What do you want? You can choose. Okay, good. Then this problem is assigned to you. But if you want, Pau can do this, Joaquin can help you, okay? And this should be the first problem. I agree with you. This was a very good question. I am very thankful. We should include this computation in the list of problems. Thank you very much.
Oh, yes, thank you.
Okay,
yeah, maybe
so if you succeed and you want to go on the Raju, let me know.
Yeah, would you agree that maybe a more physical way to tell that you try to fabricate constant of motion that always commute with the Hamiltonian? So in whatever system you are, you try to find constant of motion and they will always commute with the Hamiltonian. And that is how you generate constant of motion. So yeah, that's the main philosophy, and then you do it. Like of course.
Exactly, Raju, exactly. That was my point. That was the point in which I say, look, the only thing I was telling is exactly that was my point. But thank you very much. I was saying, look, we have S3. S3 has this invariance. Let's use this invariance of the sphere to guess which are these constants of motion. So I agree with you. The point of view comes from physics.
Right, but a related thing, because in the two-body problem that you showed, I don't remember, like there was a constant of motion which was momentum, another was angular momentum, but it was
the linear momentum. Yeah,
And the angular momentum, yeah, but that is what you were loosely telling, like Kepler's problem. Was that in an inverse square potential or in a sense of a potential? Because in inverse square potential, there is another constant of motion called as Lenz's vector, Runge-Lenz's vector.
I totally agree. And that's indeed, thank you very much, Raju. This is, as I said, I mean, I was maybe born as a mathematician, but with regrets towards not being a physicist. This could be a definition. So what you're explaining, Raju, is fantastic, because these are three constants of motion, right? But you have to have some dependence, so you can choose. And from you can choose. And this is well explained in this book, and also in another book. That's very good. And also in another book, I don't know if we put this in the notes. I wanted to add this example in the notes, but I don't know if I added. But this is explained in this book. So you have a dependence of this quotient of motion. They are not independent. That's the point. But you can choose. Sometimes you can choose. So from a physical point of view, I mean, indeed, this would be a guided problem in the list. The notation I used for this, I didn't borrow it from this book. I learned it from another book. Now I don't remember, in physics, in KAM. And I learned it from that book, and there is also explained the Lenz's force. Yeah. So you have some, this could be an exercise in the list. Raju, thank you for your participation. It's very appreciated. So indeed, you are going to see this example of Penrose in the next class, in the next theoretical class, which is now next Thursday. So yeah, for the people who connect,
I am afraid that maybe I have to miss like the next couple of classes because I have to travel in Brazil for some. Yeah, but I have to.
But they are going to be online. Yeah, you are going to be able to recover them online, because now, so I put them in the website. They are also on my YouTube channel. So from people from China can use the Chinese Zoom with the password, and you can check the channel. So maybe if you check the channel, maybe I leave some questions for Raju when I say now that Raju is going to see it afterward. Maybe I leave some questions so you can put it in the chat afterwards. Yeah. Nice. So that's for, in any case, that's for letting you know if you cannot connect.
Yeah, but the last class I will be there, last class,
okay.
And then I will write to you about the Penrose if there is any possibility of collaboration. Yeah, I will write.
Yeah, of course. Yeah, of course. This is amazing.
But thank you for this inspiring set of lectures. I learned a lot and I appreciate it.
Thanks. My appreciations to you and to your question. It's fantastic. Yeah. Okay, well, and also this other thing about the B cotangent bundle and using the B Dirac, this would be fantastic. Yeah, this was
another thing. Like when you were trying to do this T star Rn, like there were this set of functions f1 to fn. So in doing so, like there will be singularity, right? How would you like? Yeah, probably what I'm trying to say. Let me make it more clear. Like you had this integrable system, you had these functions f1 to fn, the set of functions on a symplectic manifold, and then probably locally you are like in this Liouville torus, and you are trying to that's equivalent to a cotangent bundle on some T star of, because canonically you can map it to T star, that torus Tn in a restricted neighborhood, but and that you call zero section of that level set. But what will be those singular points of that df degeneracy locus df equals to 0?
So the degenerate locus, you don't see. I mean, well, first there are two things. This model of the cotangent bundle, indeed, it's a way to look at this theorem as a cotangent leaf. This is one of the problems in the list. Indeed, it's a corollary of the theorem, and that's interesting. But then when you look at it globally on the compact manifold, these singularities have to be there. The magic thing in the toric case is that these singularities can only be of elliptic type. This is something that it's outside the contents of this class, and I was starting to talk about in this direction. And if you realize in my class, I said no, I will not talk about singularities, but the singularities have to be of elliptic type. So you need to
elliptic. Because in simple harmonic pendulum there are hyperbolic singularity. I thought like maybe this will be hyperbolic, but not
hyperbolic. That's exactly. Indeed, Pau has some beautiful prop. I mean, there are like also focus singularities that Joe Palmer is an expert of. Now he left, but he was connected here, and which are called the focus. And these are happen on the spherical pendulum. And then you have, we have a question by Robert Spark. Okay, we will get to that. And you have also hyperbolic singularities. What's fantastic, Raju, is that if you have a toric manifold, these singularities can only be elliptic. The reason of that is that there is something, I mean, if you have a group action in a neighborhood of a fixed point, you can prove that the points in the outside have to be the points in the outside of the polytope, the pre-images have to correspond to fixed points of the action. This is something easy to see because you have to increase the isotropy. Remember that these are quotients, okay? So the bigger is the isotropy, the smaller is the orbit, okay? You have this kind of control, but this corresponds to the, you know that it's the quotient of a torus. So if it's the quotient of the torus, the orbit can only be S1 or a smaller torus or a point, okay? And this corresponds, and these points, if it's a point, it has to be a fixed point. And then there is something, if it's a fixed point, you can linearize this. And this is something that already Bochner knew. Bochner had linearized group action in the neighborhood of fixed point. But the magic comes. Can you do this simultaneously with the symplectic form? Of course, because with the path method, you can do everything, you can average and do everything in bar. And this is indeed a theorem, which is usually called Guillemin-Marles-Stenberg, about what is the expression or what is the local normal form of a group action in the neighborhood of a fixed point. And this is a particular case of what happens in the neighborhood of an orbit, which is the symplectic slice theorem. Exactly. I'm giving you a little bit the framework. This justifies that you can only have, you use this theorem, and then this theorem is telling you how the moment map looks like. And then it's a sum of squares. It's a sum of squares together with some weights of the action. Therefore, it can only be elliptic. So you cannot have hyperbolic singularities in a toric action, in a toric manifold. And you cannot have also these focus singularities, which are so important, like the image is like a pinch torus that you have in physics, like in the spherical pendulum, because you don't have such a thing in toric manifolds. Let's say like toric manifolds are the easiest class of singularities that you can find to understand. Also from a point of view of geometrical quantization. Unless you understand how to desingularize these things. This would be the topic of a different course, because this would take me very far. But I don't know if you're happy with this question. Okay, I will miss you, Raju, in the next couple of lectures, but we will see you again on the last day. And thank you very much for your participation. I have a raised hand by Sparks, who I don't see
hello,
now.
Teacher. I want to
Robert,
ask you a question.
Yeah.
If I want to learn more about toric manifold, what preparations do I need to do? And I can read what books?
Yes. What is the best reference, Robert, for toric manifolds? That's a very good question. That's a question that Pau and I were asking ourselves 2 days ago. I think that if you want to learn toric manifolds, the most appealing book is the one of Anna Canas. But this depends, because if you are a symplectic geometer, first step, Anna Canas' book. This book, it's in the list of reference of the course, and it's on the website of Anna Canas. You just need to follow that book. That's the first reference. But then, if you want to understand more examples and so on, I think you need to go to more sophisticated books. There is a list of sophisticated books in the study of toric manifolds. Guillemin has one in Birkhäuser, which is very good, which is called like Hamiltonian actions. There are 2 books that I should say. Do I have them in the shelf? Why I don't have them in my shelf? One is the one by Michel Audin, which is called The Topology of Torus Actions. This is a fantastic book. I would maybe put this book before the one of Anna Canas. And then another book by Victor Guillemin in Birhäuser, and Victor Guillemin and Shlomo Stenberg, which is the torus, what is called? Torus Hamiltonian actions. I must have this in my shelf. I don't know, because I don't have it inside here. I have it in another room. So I have this at home. And my recommendation would be to start with the anacanas and then use the one of Michel Oda.
Yeah.
Okay, that's my recommendation. And then of course, Robert, what's very important, don't miss the class of next Tuesday, because Pau is going to explain you the polytopes thing, I think, in a very comprehensible way. And Pau has Pau and Joaquin, both of them, explain very well. Indeed, they explain better than I. I mean, they should take over and do this course. But so far, Pau is going to really explain this in a way I think that you will appreciate, because he will use a lot working in the image of the moment map with the polytope. So it's going to be linear geometry, right, Pau? Can we say it like that?
Yeah.
Well,
yes.
Okay. So I think, yeah. Thank you. Thank you for your participation. Thank you all. Your questions were very important for us because it makes us improve the material we are providing. So let's stop here. It's not bad. We are making very long sessions, but thank you very much for your questions. So next Tuesday, we have this fascinating problem session. This afternoon, the list of problems without the solutions of the next session will be online. Okay, this afternoon, let's say in a couple of hours, because now I asked Pau and Joaquin to add. Raju has another question. Raju is not asking a question, he's clapping. Thank you very much. Okay, guys, it's fantastic to have you there every Tuesday and Thursday. Keep on working and have a nice day. Have a nice night for the ones in China, and see you very soon on Tuesday. I will be with the popcorn guys there. Don't forget to find names for my popcorn guys in my sofa. Okay, see you soon. Have a nice day.
Thank you.
Thanks a lot, Jiang Li. Thank you, everyone. Bye, Robert. Bye, everyone. Ciao.